things that we should probably talk about to discuss matter is the kinetic molecular theory. Matter is composed of small particles, and those particles are in constant motion. So that's what kinetic means. We're talking about energy of motion. Particles are colliding with each other and the walls of their container. So when we have a gas, they're bouncing off the container. We have a liquid, the particles are moving. One of the ways that we can show this is through Brownian motion. And one of the stations for our lab, we add food coloring to a test tube of water, and we don't shake it or anything, and we can see that the food coloring will continue moving throughout the solution to help support that idea that the particles are in motion and that Brownian motion is taking place. The average kinetic energy equals temperature, or the speed of the particles. So temperature is involved in the rate of motion of particles in matter. Particles do move slower at a lower temperature, and if we get down to absolute zero, which is 0 Kelvin or negative 273 degrees Celsius, we get to that point where all particles stop moving. And that's where the Becks came in. The Bose-Einstein condensate comes in is at absolute zero. So everything does stop moving and we get the super solid idea. We'd already talked about the changes of state, or the different states of matter. So we have the solid, liquid, and gas, and those are due to the changes in kinetic energy of particles. So the hotter it is, or the increase in temperature, we do get faster moving particles, and they are able to overcome those attractions between the different molecules or atoms within that piece of matter. So what is matter actually made of? All matter is made up of elements or compounds, if we're talking about pure matter. And matter is anything that has volume and mass. So anything that takes up space and has mass is considered matter. Therefore, light or fire is not really something that we would say is matter, that is energy. We can have pure substances or mixtures. So we're going to focus on the pure substances first with elements and compounds. An element is our fundamental material consisting of one type of atom. So every element is made up of the same types of atoms. We already learned about isotopes, so not every atom is exactly the same, but they are made up of the same type of atom, meaning they have the same number of protons. So hydrogen, and we have iron, which is Fe, hydrogen is H. Notice the H in hydrogen is capitalized, and for iron, the first letter is capitalized and the second is lowercase. If you start writing everything in all caps and you don't use proper lowercase letters, they will be marked wrong. There are 120 elements total. There are some elements that are in debate as far as whether they exist or not due to the longevity of them being stable, or if they produced another element in the process. So there are some that are still in debate, but we have seen them and observed them through making them. Our periodic table is arranged by atomic number, or the amount of protons, and we did talk about that a little bit when we talked about the isotopes and ions. So the number of protons is the atomic number. So elements are made up of atoms, and that should be a review of Dalton's atomic theory. And the atom is the smallest part of an element that has all the chemical properties of that element. Molecules are two or more atoms that are bonded together. We often reserve the word molecules for covalently bonded substances, and that'll be our next unit when we talk about covalent and ionic substances. So we have the same element, oxygen, which is O2, so it is sharing two pairs of electrons. It is a double bond between the two oxygens. And then we also have different elements, carbon monoxide, carbon dioxide, or water. So we have two different elements, or more than one atom of many elements, or of the same element. So that would be molecules. We also have compounds, the materials in which atoms of different elements are chemically bonded. So sodium chloride and sodium and chlorine join together to form NaCl table salt. Compounds do have properties that are different from the elements they are made from. So sodium is a somewhat soft, grayish metal. It can be cut with a butter knife. It's still painful to do that, but you can slice it with a butter knife. And then chlorine is a gas, and it's a colorful gas. And when we have those bonded together chemically, we get that beautiful, clear, colorless crystalline structure, table salt. If you were to put sodium, raw sodium, in your mouth, it would explode with the acid in your mouth and catch on fire. Chlorine gas, and if you inhale that, it'll make you extremely sick. But however, table salt, we can eat that, and it's added to a lot of our foods as preservatives or for flavor. So the compounds do have different properties than the elements from which it's made. Now, mixtures are different than compounds. Compounds are chemically combined. Mixtures are different substances that share the same space. They are physically combined. You can separate them, sort them, and do different things to get them apart. Whereas a compound, you can't just pluck atoms from each other and say that you're sorting those. It doesn't work that way. You have to undergo a chemical reaction to do that. We have mixtures of elements, so like stainless steel consists of iron, chromium, nickel, and carbon, so that is a mixture. And we have mixtures of compounds where we have sparkling water, which consists of water, H2O, and then there's mineral salts, and then we have carbon dioxide added to it to make it bubbly. So there are different mixtures. Not every mixture, even the same components going in, doesn't mean they're the exact same ratios. So we'll look at some mixtures in the lab or in the classroom. There can also be mixtures of elements and compounds. So if we think about our atmosphere, our air, we have oxygen, which is an element, nitrogen as an element, carbon dioxide is a molecule, we have water vapor, and there are many other gases within our atmosphere. So there is a mixture that we are breathing for air in our atmosphere, and it's made up of many different things. Keep in mind, a mixture is separated by physical means. So you physically put them together and you can physically take them apart. It does not mean that when you put them together, they're going to lose their identities or properties. So when we make Kool-Aid, we take that wonderful powdery mix and add it to water, and the color, is much more vivid. You can see it. It was there before. It was just hard to see, and then it's there. And then we can take that Kool-Aid and we can evaporate the water off from our liquid mixture, and we can collect the water from that, and we'd be left with the crystals. They won't be exactly the same because they weren't ground up, but we will have crystals of the flavor and the color and sugar and other things that were added to it. There are different ways that you can separate mixtures. Most of us have used filtration at some point in our lives. If you're making macaroni and cheese or spaghetti, you filter the noodles and the water. You pour the water off in a colander. Evaporation, we do that when, if I think of rice-a-roni and pasta-roni, you have your water in those with your noodles or rice, and then you heat it so it boils and the water evaporates off so the flavor gets evenly distributed and you can cook your noodles and your rice. Also distillation, and that is something that we use temperature to do with evaporation or boiling points. There is chromatography. We'll dabble with that a little bit, looking at different chromatographies for ink, so that's something we can demo one day. Then there's also magnetism, so we can pull mixtures apart based on if it's magnetic or not. Distillation is where we have a liquid mixture or a solution, and we can evaporate the liquids off. So we can do that with different boiling points of liquids or melting different boiling points of liquids, and if there are solids that are in there, they'll remain in the container. So we can evaporate water from seawater, salts will remain. So evaporation or distillation. So what we're going to look at is a distillation apparatus. And the picture, is out of order here. So there is our distillation apparatus. You will see at the bottom we have a Bunsen burner in the bottom left, our heat source. And then there's a round bottom flask sitting over it. So there's our liquid that we want to separate. It's connected to a tube and a thermometer sticking out the top. You can see that it's labeled there. So it does depend on temperature. So you can't just crank that up there and expect it to separate. You have to monitor the temperature, or you can just boil everything in there. And then we have our condensation tube. So we have cold water going in the upper area where that little spout's sticking out on the bottom of it, and then it runs out the bottom of it. And some people hook so the bottom is the inlet, and then it runs out the top, so that way the tube feels better and it's completely surrounded. So what happens is your liquid gets boiled. You have a certain temperature, so maybe we have a mixture of alcohol and water. Alcohol is a lower boiling point. So we heat it up to that temperature. The alcohol will evaporate and it goes up into the tube. And then you have your condensation tube, which is cold, and the alcohol will condense, make little droplets, and go in the tube. And notice it's at an angle, so those droplets can run down the tube using gravity and then drip into your collection flask. And then you will have the alcohol in the collection flask, and you would have water in the brown bottom flask that is being heated. So that is a distillation apparatus, and we won't be using that concept actually in class. We may try it, but that is something that I think they do use in AP, and it's one of those stereotypical things they put in labs and TV shows and movies. So that is a distillation apparatus.